All right, let's jump right into this explainer and build a really solid physical intuition around the foundational laws of thermodynamics. Now, I know thermodynamics is one of those subjects that sounds a bit intimidating, but it actually governs almost everything we interact with on a daily basis, from the coffee sitting on your desk right now to the engine in your car. We're going to break down the actual real-world physics of heat, temperature, and exactly how matter responds to thermal energy.
But before we even touch the complex math, we have to start by challenging some of your everyday assumptions. Like, what is the actual difference between temperature and heat? We use these two words interchangeably all the time in normal conversation, right? But in the world of physics, what hot and cold actually mean is probably going to surprise you. So here's the deal. Temperature is literally all about motion. Specifically, it's a measure of how fast the microscopic particles, the atoms and molecules inside a substance are moving around. Faster particle motion, that equals a higher temperature. Heat, on the other hand, is a totally different beast. Heat isn't just some property that an object holds onto, it's the actual transfer of energy flowing from a hotter object to a colder one. Basically, heat is energy on the move.
Here's our quick roadmap for today. First, temperature versus heat. Second, the Zeroth Law. Third, measuring temperature. Fourth, thermal expansion and stress. And finally, specific heat.
Section 1, temperature versus heat, when energy stops flowing.
This brings us to a really fundamental concept in physics, thermal equilibrium. This is the specific condition when interacting objects reach the exact same temperature, and because of that, heat completely stops flowing between them. Think about it practically for a second. If you stick a room temperature thermometer into a hot cup of coffee, the thermometer obviously gets hotter, and the coffee actually cools off a tiny bit as that energy transfers from hot to cold. But eventually, the whole system settles into the state of thermal equilibrium where no further change happens. And you know that steady value you're looking at? That's what you're actually reading as the temperature.
Section 2, the Zeroth Law, the balance of thermal energy. Okay, imagine an insulated box containing three distinct systems, A, B, and C. In our first scenario, blocks A and B are separated by an insulator, meaning they absolutely cannot exchange heat directly with each other. But both of them are touching system C below them through a conductor. Give it some time, and A and B will both individually reach thermal equilibrium with C. Now, for the second scenario, we test them against each other by separating C with an insulator and connecting A and B with a conductor. So what happens? Well, absolutely nothing happens. And honestly, that is exactly the point. This gives us the Zeroth Law of Thermodynamics. It simply states that if system C is initially in thermal equilibrium with both A and B, well then A and B are also absolutely in thermal equilibrium with each other. So the crucial takeaway here is that two systems are in thermal equilibrium if and only if they have the exact same temperature. This simple, completely logical, transitive property is literally the very reason thermometers work. We don't need to directly compare the temperature of every single thing in the world to each other. We just compare them all to a standard thermometer. Section 3, measuring temperature, tools for equilibrium. You know, you're probably super familiar with the standard mercury in glass thermometer. A lot of basic thermometers work on a really simple but profound physical principle. Materials almost always expand when they get heated. As the liquid mercury, or ethanol, in that thin glass bulb heats up, it expands, literally pushing liquid up a highly calibrated, extremely narrow capillary tube. The actual amount of that physical expansion is directly proportional to the change in temperature, which is what gives us that reliable visual readout. It's actually really fascinating to map out the three major temperature scales directly against each other: Celsius, Fahrenheit, and Kelvin. Notice how they all have completely different starting points. Celsius sets its 0 at the freezing point of water and just neatly divides the gap to boiling into 100 equal degrees. Fahrenheit does its own thing, setting freezing at 32 degrees and boiling at 212, which gives us 180 degrees between them. And Kelvin? Well, Kelvin aligns perfectly with the Celsius degree size, but it shifts its 0 point all the way down to absolute 0, which is why it's used so heavily in scientific calculations. To really anchor these scales, we use a few absolute milestones. 0 Kelvin is absolute 0. That's the lowest possible temperature in the universe, where particle motion essentially just stops. Then, of course, we have the standard freezing and boiling points of water, but the most important one here is 273.16 Kelvin, or 0.01 degrees Celsius. This is known as the triple point of water. It's this incredible, exact, unique combination of temperature and pressure where solid ice, liquid water, and water vapor can all stably coexist at the exact same time. Because of its insane precision and reproducibility, this exact state is used as the foundational reference point for defining the entire Kelvin scale. Section 4. Thermal expansion and stress. Physical consequences. Like I briefly mentioned with the thermometer, most materials get bigger when heated and shrink when they cool down. We can perfectly visualize this linear expansion by just imagining a solid rod stretching out along a single dimension. When the rod's temperature goes up, its initial length, which we'll call L0, grows by a specific amount we call delta L. And that change in length is directly proportional to the change in temperature.
And here are the exact mathematical formulas that dictate exactly how much an object is going to expand. For linear expansion, delta L equals alpha times the initial length times the change in temperature. Now, alpha is just a specific coefficient that depends entirely on what the material is made of. Copper is going to expand differently than steel, for example. And for three-dimensional objects, we use volume expansion, where the change in volume equals beta times the initial volume times the temperature change. Interestingly enough, for your standard solid materials, beta is literally just 3 times the linear coefficient alpha. These equations just prove that thermal expansion is completely mathematically predictable.
But hey, what happens if we don't let it expand? Well, that brings us to thermal stress. If you rigidly clamp down the ends of that rod to prevent it from expanding or contracting as it changes temperature, massive structural forces start to develop inside the material. The material is essentially fighting itself. The resulting thermal stress, which is driven by the relationship between temperature changes and the material's structural elasticity, can be powerful enough to permanently deform or even violently snap solid metal. Section 5. Specific heat. Calculating required heat. Enter specific heat capacity. In physics, we denote this with a lowercase c. This is defined as the amount of heat energy, which we call Q, required to raise the temperature of 1 single kilogram of a specific material by exactly 1 degree Celsius. Just like those thermal expansion coefficients we just looked at, specific heat capacity is an inherent, baked-in property of a material. And the master equation here, Q equals mc delta T, is your absolute key for solving any heat transfer problem. Heat equals mass times specific heat times the change in temperature.
Let's actually plug some numbers in and see how this builds into a real-world calculation. By breaking the math down into these really simple sequential steps, solving for heat is a breeze. Step 1. Our goal is to find the heat needed to raise just 2 kilograms of water by a mere 5 degrees Celsius. Step 2. We set up our master formula using water-specific heat, which is actually quite high, at 4,200 joules per kilogram degrees Celsius. Step 3. We calculate 2 kilograms times 4,200 times 5. The result? It takes a whopping 42,000 joules of energy just to warm up a couple liters of water slightly. Pretty crazy, right?
So given these truly massive forces and highly specific energy needs, how do thermal expansion and specific heat dictate the engineering of our bridges, our engines, and really our entire daily environment? I'm going to leave you with that provocative thought. Next time you drive over a bridge and hear your tires hit those clanking metal expansion joints, or even when you just start the engine of your car in the morning, take a second to consider the invisible, powerful thermodynamic rules we just explored. They are constantly at work, transferring energy and keeping our modern structures completely intact. Thanks so much for diving into this explainer with me, and keep exploring the fascinating physics all around you.